Good morning, good evening, everyone. Welcome to the Vitis Acceleration webinar. In this webinar, I will introduce a simplified Vitis embedded extensible platform creation flow. Today, we will recap the Vitis platform basics first. We'll use a normal platform creation flow, then dive into the details about platform workflow simplification. At last, I will demonstrate the simplified workflow. The discussion and demonstration will be based on Vitis 2022.1. The Vitis platform is an important concept in Vitis designs. When we talk about Vitis platforms, especially in embedded use cases, we usually mean Xenix Runtime and Vitis Target Platform together. They provide the unified programming interfaces to applications and makes deployment target transparent. There are differences between data center use cases and embedded use cases. Because in embedded use cases, we need to provide the embedded operating system and components. The target of the Vitis development environment is to help developers focus on their application development. So we package the operating system, XRT, boot components, and target hardware design all into embedded platforms. If we classify the platform types, data center and embedded platform can be the two major types. Data center platforms work as an accelerator for x86 CPU hosts. x86 CPU control data center cards through PCIe. Embedded platforms can work by themselves. They don't need external host processors. If application needs to extend their hardware function, the platform needs to be an extensible embedded platform. For example, Vitis AI applications require extensible embedded platforms to add DPU to hardware. AI engine applications require extensible embedded platform to add data collections. If the hardware functions required by the applications have already been implemented in the platform hardware, the embedded software development platforms can be used to develop the software applications. Since the embedded use cases can be varied from each application, embedded platforms are fully customizable. Today, we will focus on the embedded extensible platform. Here is a diagram of typical embedded system design. The AI application and the DPU kernel are the main part of the application. The other components are the supporting functions for applications. So we package them together into the Vitis platform. It contains the hardware part and the software part. The hardware part defines the peripherals and supporting IPs, such as clock generator, envelope controller, and the memory controller. The software part provides the application running environment from boot component to Linux and Xenix Runtime. The software part provides the application running environment from boot component to Linux and Xenix Runtime. The embedded design can be abstracted to this three-layer architecture. The operating system, drivers, and runtime is the software layer, plus the hardware design layer constitute the Vitis platform. It provides the running environment support for the application layer. This layer separation environment couples applications and low-level hardware. Application or PAR developers can focus on the algorithm by taking hardware as a set of given interfaces and API. Platform developer can dedicate on the platform deployment. This kind of layer separation and abstraction also make the data flow standardized. Standardize the interfaces between the platform and the applications from a set of common rules, which makes the applications and the platform cooperate with each other. The hardware part provides the interval signals, clock and reset signals, and XA interfaces, such as XA memory interfaces, XA control interfaces, and XA stream interface for kernel. With ++ will interpret kernel with the hardware according to your user's hardware link configuration. On the software side, XRT provides the API interfaces for applications. User can use the XRT native API to program applications. XRT will translate the command to control the pure kernels. This kind of architecture makes a platform reusable, which means a platform can support different applications. In one case, we can program DPU kernel to support AI recognition application. In another case, we can switch the kernel to support object detection acceleration. The platform can serve these different kernels well because these kernels only require fundamental platform features like local DDR memory access for data storage. This kind of architecture makes the apps portable as well, which means one application and acceleration kernel can be applied to different platforms with no code change. For example, the object detection and acceleration kernel can be applied to the ZC104 platform. Embedded platforms like VSK190-based platform can also work well. Similarly, the application developers can easily port their applications and acceleration kernels to other platforms with the same interface. For example, when the board updated the DDR capacity, it only needs to rerun implementation after updating the platform. The application code doesn't need to change. The kernel and the application can work with both the two platforms or can be easily ported to other platforms. Because the kernel requires basic IC interface or memory access can be provided by the platforms. When designing the platform hardware, you may encounter a question whether this function should be added to the platform or be linked as a kernel. We have some recommendations. Please refer to the UG 1933 for detailed information. Now we know the platform basic concept. We can start to discuss the platform creation flow. First, let's find out the platform components. Platform consists of hardware component and software component. The hardware component is the XAC file, which is a Vivado design with all the IP functions and special metadata properties. The software components contain Linux components such as kernel image, root file system, device tree, and system root, which is usually used for host application cross-compiling, and the boot components such as untrusted firmware, U-boot, and device tree, which makes the kernel boot properly. Next, we will discuss how to generate these components. From a high-level point of view, creating a customer platform is to prepare components. Most of the components can be provided by the base football design. A base football design with Vivado and Python Linux image that can boot the hardware to Linux OS could give a platform creation a good start. It's important to make sure your base football design is correct before going forward, because it could give you clues to isolate the root cause if the generated platform encounters any issues. Peripherals, including memory and hardware, should be tested by this football design. Once the base football design can boot properly, we can start hardware settings for platform requirements. In this stage, in order to make the hardware design comply with the wide platform requirements, we need to check whether it can provide clock, reset, interrupt, and exit interface. One clock and its associated reset signals are mandatory, because without the clock, kernel cannot work. If interrupt is not available, XRP will run in polling mode. In general, interrupt is recommended because interrupt mode would allow processors to work on other tasks instead of checking kernel status regularly. Exit interface can provide a control channel and a data channel between kernel and platform resources. Usually, we will provide an exit master to control kernel start and stop. Kernels need to access memory. Memory controllers are instantiated in embedded platforms, so the platform needs to export the exit slave interface so the kernel can use the memory. Exit streaming interfaces are good for streaming data, like audio, video, ADDA. It doesn't have address info, like memory map exit. For example, MIPI core generates exit stream. HDMI reads the exit stream. For video processing platforms, we should export these exit stream interfaces for kernels to process. And last, we can export the XAC file. After XSA file is ready, user can start preparing software components, including Linux-related image, such as Linux kernel image, DTB, root bus, and system root, and also the boot components, such as untrusted firmware, U-boot, and DTB. Linux is required because the execution kernel needs to be controlled by XRT, which currently only supports Linux on ARM. If you already have a working Linux environment from the base bootable design, you need to update your software environment to enable XRT support. After hardware and software components are ready, user can link them together and create their Vitis platform XPFM file. The platform creator should verify the platform before delivering it to application developers. Combined with the tools and components, the creation flow is like this. First, utilize the Vivado to do the hardware design and export the XSA file. Second, use Python Linux tool to configure and build the software components. Third, generate the Vitis platform XPFM file with Vitis. Last, validate the platform with Vitis. We know the platform creation flow. Let's dive into platform creation simplification. As we know, when create an embedded acceleration platform, you need to set up the clock, reset, exit interface, and interrupt every time for every acceleration platform. Some customers told us this process is a repetitive work and takes a long time to complete. You will encounter issues related to collections or configurations. Besides, to some customers who are dedicated on application development, want to create their own platform with basic functions to validate their application. It is not friendly and a little complex for them to create a platform from scratch. So, in order to make it easier for developers and users to create a Vivado-based design and expedite the process of Vivado project, we prepare the customer extensible design, short name is CED, which packs the acceleration platform basic setup and configurations, such as clock, reset, and exit interface, together into a basic design, and support all the Z chipset like Versal and ZKMP. In Vivado, by clicking the Open Example Project button, you will get the CED preset selection setup dialog. After confirmation about the clock and interrupt, you will get the block diagram. In this block design, it has already set up the clock and reset system, interrupt system, DDR4 configuration, AIE block, PS set peripherals, and export the exit interface. That means you can export the XSA file directly without any other setup and configurations in Vivado design state for basic platform. Regarding using Python Linux to build their software components, we frequently heard problems from customers. Some customers said they encounter issues about lacking dependency of libraries or running out of memory when building the image. Once, one customer's feedback impressed me a lot. He said to us, hardware background engineer, I don't have experience of Linux, and of course don't know how to build a Linux image. If studying Linux, it would take a long time. The customer hoped we could help them to solve this, because there are many similar situations like that. I fully understand this, because Linux is totally different from hardware design. It needs extensive embedded knowledge to handle all the possible issues. So, in order to make hardware background engineers or new users who don't know how to use Python Linux can make a platform with basic functions, we add an easier method to prepare software components instead of using Python Linux. As we know, except for the device tree, which is strongly hardware related, all the other software components are generic and reusable for other devices with the same chip series. So, we extract the images which are generic and reusable, such as the kernel image, root bus, and system root, to a common image package. We also prepare a new command, createdts, for user to create the directory file which is highly associated with corresponding hardware. Regarding the common image, user can download common image package for Versal or ZKP from Linux Download Center. After you decompress the package, you would gather most of the software components. Among the common images, bear31.ef is untrusted firmware. Boot.sar is used by UBboot to detect the boot device and boot from corresponding device. Image is the Linux kernel. rootfs.ext4 is the Linux root file system in Linux format. rootfs.manifest is used to tell user the content of rootfs. rootfs.tat.gz is the zip file of Linux root file system. sdk.sh is the cross compile tool to compare host application. u-boot.ef is the bootloader used to boot the device. readme.txt is to tell user the content of this package. You may know, in previous version, if user need to generate the directory file, user need to perform several steps. Download the directory source code, create a platform and build the platform to get the peer set preference, then compare the directory file. It's a complex and inconvenient for user. Now, we can generate a directory file with one command, createdts. Here is a usage example. This command has several options. Hardware, platform name, and output directory are mandatory inputs. Hardware is the XAC file which contains hardware information of your platform. With the local option enabled, it can automatically generate the local node, which will be used to bind the XRG driver in Linux system. The compare option is to generate the DP binary file directly. In a word, you need to prepare a Python Linux tool and build all the software components with Python Linux in 2021.2. Now, what you need is to utilize the createdts command to generate the directory file. Other boot components and the Linux image are ready for use. In a summary, this is a simplified creation flow. Utilize the CD design and export the exe file directly. Navigate the common image and use createdts to generate DB file. Then generate XPFM with the software and hardware components. From 2022.1, we suggest users use common image and createdts command to generate the software components. However, if user need to customize the Linux image, Python Linux would be the best choice. Let's demonstrate the simplified platform creation flow.
Let's start our demo. First, create a workspace for our project. Then go to workspace directory. Launch Vado. Because I have already set up the Vado and Vitis environment in my server, so I can use them directly. User need to set up the environment before using it. Then click Open Example Project. Click Next. Select the Versal Extensible Embedded Platform. Next. Set the project name. VCK190-hardware-platform. Please keep the Create Project Subdirectory option enabled. Next. Select VCK190 evaluation board. Next. This is the preset selection page of the CED. You can change the clock, interrupt, enable the IPDDR4, disable the AI engine block according to your requirement. In this demo, I will use the default setting. So next. Review the project summary. Finish. It will create a project. This will take about 1 minute. Okay, the project is ready. Let's check the project settings first. You can see this project is an extensible Vitis platform. Click OK. Let's have a look of the block design. You can see it has already set up the clock and the corresponding reset signal, AI engine block, interrupt, lock DDR, Versal. Then go to Platform Setup tab. You can see it has already exported 3 clocks, enabled the interrupt, export the exit port, exit slave for DDR access, exit master for kernel control. Then we can generate block design. Choose global because it will skip IP synthesis during generation and it will save some time. Generate. Okay, it finished. Please ignore this warning because this pin will be collected by V++ to kernel in step 3 when you create an PL application. So click OK. Then we can export the platform. Next. If you want to do hardware emulation, you can choose hardware emulation. This demo, I choose hardware. Next. Next. Please set the platform information. Next. Please set the XCC file name. In this demo, I will use the default name. Next. Finish. It will take about several seconds. In the Tico console, you can check the XCC file is ready. Then we can start to prepare the software components and generate a Vitis platform. From 2022.1, we suggest users to use the common image and createdts to prepare software components. So, before using the common image, we need to download the common image from the Linux Download Center for Versal or ZenkMP. I have already downloaded the common image for Versal, so we can use it directly. First, create a directory for the Vitis platform. vck190-custom platform. Go to this directory. Extract the common image. To the current directory. Okay, you can see there is a Linux-Versal-common directory. It contains the content. Then we can start to prepare the DTB file. First, start the XSCT tool. Create. We can check the command usage -help. You can see the command usage and its example. I have already prepared one command to generate the DTB file. You can see That's hardware to specify the XSA file. That's out to specify the output directory. That's local to enable XRT support. Platform name. Get branch because we want to use the latest device tree file. That's board to specify the board because we want to use the VCK190 board's device tree file. Add one option, dash compare, because we want to get the DTP binary file directly. If you don't specify the compare option, you will get the device tree source code, then enter. It will take about several seconds. You can see it is generating the device tree. Okay, it finished. Exit the tool. We can check the DTP file. VCK190 PS device tree domain BSP. Here you can see system.db file. Then we can start to generate a Vitis platform. Before generating the Vitis platform, we need to prepare two directories. Boot directory is to store the boot-related components. SD- directory. This directory is to store the FAT32 partition-related file. Then copy corresponding file to the directory. Copy Xenix u-boot to boot directory. Copy Xenix bl31.df to boot directory. Copy ps device tree bsp system.dtb to boot directory. Copy Linux boot.sar to sd-dir. Boot.sar is used by U-boot to detect the boot device. Then we can start Vitis. Select the workspace. Select VSK190 customer platform directory. Open. Launch. Click Create a Platform Project. Set the project name VCK190 dash platform. Next. Select the XSA file. Go to Workspace, VSK190 hardware, platform, XSA file. Open. Change the OS to Linux. Finish. OK. Then we need to set the Linux domain. Generate a BIF. BIF file is used to organize the boot components. Select the boot components directory. Boot. Select FAT32 partition directory. SD-dir. Open. then click Build. Build finished. We can do a simple test to test the platform. There is a tool named Platform Info. It is a utility of Vitis VCK190 platform. Export VCK190. You can see the platform information about the platform, location, chipset, exported 3 clocks, Linux domain, lib file, and components. Also, you can use a Vitis GUI template like VAD to create a simple PR kernel to test your platform. In this demo, we focus on the simplification, so I will not do the test. Thank you.
We have provided the source code and the documents for embedded platform creation in Vitis-Tutorial Github repository. Please refer to them to find more details. You are welcome to ask questions with GitHub issues or contribute through GitHub pull requests. Thank you for watching.